Why is orbital insertion a new dimension of movement? Imagine sending a spacecraft on a journey where it doesn't just fly past a planet or moon but begins to dance around it. That's what orbital insertion is all about. It turns a simple trip through space into a controlled, steady orbit. And like flying straight or bouncing off a celestial body, this maneuver makes the spacecraft follow a curved path held in place by gravity. It's like switching from a straight line to a loop-de-loop around a planet. This change is what makes it a new way of moving in space. When a spacecraft gets close to a planet or moon, it usually follows a transfer trajectory. This path can be hyperbolic or elliptical but isn't stable. To stay in one place, the spacecraft needs to slow down or speed up at just the right moment. That's where orbital insertion comes in. It's a carefully timed burst of engine power, called a delta V, which adjusts the spacecraft's speed and direction. This change helps it settle into a closed orbit, instead of flying away or crashing into the surface. Depending on the mission, the spacecraft can be placed into different types of orbits. It could be a low Earth orbit, which is just a few hundred kilometers above the surface, or a geostationary orbit, which is about 36,000 kilometers away. Each orbit has specific speed and altitude requirements. The ability to perform this maneuver transforms the spacecraft's movement from a one-time pass into a continuous loop around the celestial body. This allows for long-term tasks like taking pictures, relaying signals, or studying the planet or moon over time. Orbital insertion is essential for many space activities. Satellites need it to stay in place for communication or weather monitoring. Space stations relying on it for resupply missions. Robotic explorers use it to orbit planets and gather data. Without this maneuver, spacecraft would just fly past or crash, making sustained operations impossible. It's a precise process based on Newton's laws of motion and gravity. Engineers calculate exactly how much thrust is needed and when to fire the engines, ensuring the spacecraft arrives at the right speed and position. In essence, orbital insertion introduces a new dimension of movement because it allows spacecraft to switch from a fleeting journey to a stable, repeating path around a celestial body. Instead of linear travel, it creates a continuous, controlled orbit that keeps the spacecraft in a state of free fall around the planet or moon. This capability forms the backbone of modern space exploration and satellite technology, opening up endless possibilities for observing, communicating, and exploring our universe.